So here we are with area under the curve, part 2, and we're going to be looking at left endpoint rectangles, finding area using left endpoint rectangles. This lesson here corresponds with lesson 2.3.2 and 2.3.3 in the book. So the problem that we're going to look at today here is f of x equals 2 to the x, and we're going to estimate the area of f of x over the domain of 1 to 3 using 5 left endpoint rectangles. The LEQ today is how to estimate the area. Now, in the past, we've estimated the area using any method that we like. We're going to, get a little more formalized method to do that. And again, that method is using left endpoint rectangles. The steps to success are listed here. So as I go through this problem, these are the steps that I'm going to be taking to demonstrate how to find or estimate this area. So first things first is set up the problem. Okay, so doing this problem the easiest way always involves getting it set up correctly. And in this case, we're going to be looking at this function f of x. Okay, this is our domain, 1 to 3, and we're going to use 5 left endpoint rectangles. Now again, setting the problem up, it will help make this a little bit easier, a little bit neater to look at. All right, so what we're going to do first is figure out what to count by on the x-axis. Okay, and how are we going to do that? Well, we're going to take our domain, which is, 3 minus 1, which is 2, and we're going to divide that by how many sections, which is 5. Okay, which means our x values are going to change by 0.4 each time. So we're going to start at 1, and we're going to count by 0.4s until we get to 3. So then you come over here to your graph, all right, and you can break this graph here so that we can start right at 1. So this will be 1, which makes the next one 1.4, and then 2, can't count, 1.8, 2.2, 2.6, and 3. Okay, now if you don't like it being that squished up there, let me just go about changing that a little bit, make it look a little nicer. Okay. If you already started, sorry about that. Let me back up. We'll go 1, 1.4, 1.8, 2.2, 2.6, and 3. Just want to space things out a little bit, make it a little easier to look at. Okay, now the y-axis, how high do we have to get? Well, 2 to the third is what? 2 to the third is 8. So we have to get to 8. All right, so if I count my units here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I don't even have 16 spots. So I'm going to have to count by ones. And your units on the x-axis do not have to match your units on the y-axis. There is no rule or law that says that that has to be true. Okay, so 2, 3, 4, 5, 6, 7, 8 will be the highest I get. Okay? So that's setting up the problem. Set up the problem. And again, if you set it up correctly, or if you set it up this way, it sort of just makes our life a little bit easier. The second thing is something we talked a little bit about today, and something that's going to help us down the road. It's going to set something up for later, is to label your x values. So our x sub 0 is 1, and x sub 1, x sub 2. Now the reason we start with x sub 0 is because in the future we're going to have to write this sum in sigma notation. So if we start at 0, it's going to help us write that little linear equation that's involved in that process, because figure 0, or term 0, is the y-intercept. It makes our life a little easier. Okay? So once we have the problem set up, now it's time to sketch the graph. And that's where you want to use the calculator. Okay? The calculator is going to be your friend here, and we want to make sure we use it, okay, to the best of our ability. So if I turn the calculator on, go to y equals. Okay, my calculator is not working. Technical difficulties. Let me do this here. Whoops. Oh, where'd it go? It left. All right, hold on. Now we're back. So we go to y equals. We type in 2 to the x. Okay, and we go to our table, but our table isn't really going to help us right now because it's not counting by the same units we're counting by. So we want to set up our table. So second table set. Start your table where the domain starts, which is 1. Delta table will be 0.4. Again, that's what we came up with. 3 minus 1 divided by 5. Then go to your table. And now we have the values we need to be able to graph this function. So let's see here. We got 2.6 3.5, 4.6, 6.1, and 8. Okay, so you're going to want to plot all those points. First one being 1.4 and 2.6. Okay, 4 and 2.6. Now again, counting by ones kind of stinks here on the y-axis, but you could always count by more than that. And then we got 3.5 and 4.6. So 3.5 and then 4.6, and then we have 6.1 and then 8. So 6.1 and 8. So it doesn't really look like much of a curved line when we draw it so spread out, but it is. We know it's 2 to the x. Okay, so sketch the graph. We have the graph sketched. We plot all of our points. We're going to need those y values later to determine the area, but we're ready to go now. Next step there would be to draw the left endpoint rectangles. Again, you can draw those however you'd like, but we want to go ahead and draw those rectangles in. So we're going to drop vertical lines down at each of our widths that we already predetermined and put on the graph. And they're left rectangles, okay? We're using all left rectangles here at the beginning. So, so you're always starting at that left endpoint. That means the left corner of the rectangle is going to touch the y-axis, okay? I don't know if it'll let me shade these or not. We'll find out. Look at that. So there's my rectangles, okay? My left rectangles. All right, so draw left endpoint rectangles. We got that. Check. Using of the Rogaine. Check. Next, we need to find the dimensions of those rectangles. So we already know the width of each rectangle. The width of all of our rectangles is 0.4. We should know the heights because the heights of the rectangles are just the y values. So here my y value was 2. And then it was 2.6. And then it was 3.5. And then we were at 4.6. And then we were at 6.1. And then there is no rectangle there. Okay, so I have 5 rectangles to add up. So I'm going to find the dimensions, check, estimate the area. That's the last step. So 0.4 is my width times my height of the first rectangle. We'll call that rectangle A. So it's times 2. Plus 0.4 for my second rectangle, the height is 2.6. And again, those are the y values of my function. Plus 0.4 times 3.5. Plus 0.4 times my next height, which is 4.6. Plus 0.4 times my last height, which is 6.1. And if I add all of those together, I will get my left endpoint area estimate. Now again, a shortcut to that is if we continually multiply by 0.4 like we did here, we can factor that 0.4 out in front and then just add up our y values. So that's something small that will come in handy later, and you see, or you should see, how this is going to set up the use of our sigma notation, because we're adding a bunch of numbers together. Okay, so that area estimate then would, so our estimate for the area then becomes 7.52 units squared. 7.52 units squared. And again, that's a left endpoint estimate. Is that estimate above or below the amount or the actual area? Okay, is it greater than or less than? It is definitely less than. Okay, it's an underestimate for the area because we have these empty spaces here. If we wanted an overestimate, we would have had to use right rectangles, which means our rectangles would have looked like this. And the nice thing about the right rectangles is everything about the problem remains the same. None of these values here change. Okay, the only difference is this statement from a left to a right. If I would do that statement for a right rectangle, so area for the rights, it would still be 0.4 because that's still my width. And instead of using 2 here, because there's no rectangle here, the first rectangle is up here at 2.6. So I add all the same numbers together. And this time I would actually include the 8 because there is a rectangle at 8 now. And I would calculate that area for the right rectangles. And that area there is 9.92 units squared. Okay, so we did left rectangles there with an underestimate. I went through, just gave you a quick review there of right rectangles with the overestimate. And again, like Nate said today in class, a great way to find the most accurate answer there would be to average those two together. So just to review here real quick, set up the problem. That means you take your domain, subtract your domain, divide by the number of sections, okay, which in this case was 5, and that tells us what we're counting by on the x-axis, okay? That's important because it's going to help us down the road. All right, we label those as x sub 0, x sub 1, so forth, all the way up to the end. Then we draw our graph. We use our calculator and we set up our table to match what we want, starting at 1, counting by 0.4. Okay, if we go to our table, it gives us all the coordinates we need to plot and get our graph. We draw in our left rectangles if that's what it's asking for. All right, we figure out the dimensions of those left rectangles, which all the widths are always going to be the same. The heights are the y values. Okay, and then we determine our estimate for area. If we want right rectangles, everything's the same, except we're going to start one later and we're going to end at the end.